So as we approach the end here, we have, I'll do all of chapter 10 today. There will not be necessarily problems assigned to do, like the check your understanding problems. But I'll go through today kind of what my expectations are for what you should know and how to do based on the slides that we're going to go through today. Then, and I had there in the corner, don't forget to complete the teacher evaluation. I couldn't remember if that had been hit yet or not. One semester it was when we did this, and another one it wasn't. So it'll be coming up soon when that does happen. Please fill out the evaluation for me. When you are in there, I appreciate feedback that tells me how to be better. Don't just give me all glowing results, because I know that's what you're thinking, like best ever math teacher. No. But so then we have this. Then we have a chapter on, or a section on permutations, combinations, binomials, expansion, some areas like that, which will be, again, a broader concept that we'll cover. And I'll show you exactly what we have to do in that as well for that. For those of you that are taking stats next, the combination, permutation, that day lecture notes will be very valuable for you when you go to take that class. And having some background information there. We'll do a little bit of probability in there as well as we kind of come to a close on this book. We have probably the equivalent of about 1.5 lecture times of review problems to work on. And then if my numbers are adding up correctly, there will be another day where it will be me here with drop-in help. Show up, we'll work on problems. You tell me what, bring check your understanding problems with you. And then we can work on those together. It will not be a, hey, can you reteach this topic? Or can you, professor, provide an example of this? I want you to bring example problems of what you're struggling with. And then we can work on them that day in class. And then that pretty much takes us to the final exam, which will be on Tuesday, April 29th. I sent you an email with an attachment of the exam schedule. So if you haven't seen it, it's attached to an email that I sent you. And you can figure out when all of your exams are based on that email that I sent sometime, I think it was right after class last time we met. All right, so conic sections, here we go. So 3-dimensional, here's a cone. That's why they're called conic sections. Here's a cone. Now imagine, again, my background, I come from Wisconsin, so everything to me is cheese, right? If this were a block of cheese shaped into a perfect cone, if you could slice that in any different way you wanted, what kind of shape would the cross-section be if you could slice that? All right, so you're thinking, not answering out loud, and assume that this base extends, like, essentially forever. Oop, didn't want to move that whole thing. So the whole thing is, like, fully extended. I don't like that pointer. We'll use red. So this base, right, these edges, they extend forever. So it's like an infinite cone in shape. So either draw a picture of that yourself if you can, but write down, like, how would you slice it in any way you wanted to make as many different shapes as you could. So go ahead and take a minute and make a list of all the possible lists, all the possible shapes that you think you could make by slicing that cone. So again, slicing it right down the middle through the point. So if you took that and then took that ice cream cone, if you will, and laid it open, what shape would that look like?
Triangle.
Triangle, yeah. So far, if we did it completely horizontal, we get a circle. Right down the middle, and then if we laid that open, it would look like a triangle.
Look at it at the bottom, maybe an arch, right?
Say that again, how would we slice it?
If you looked at it like same slice.
Oh, same slice.
Looking at it this way,
Well, don't worry about the bottom of it. We're just looking at, because it goes on forever, right? That cone we said goes on forever. But if we took a slice and just looked at that one slice and opened it up, it would be a triangle with an infinitely extending base. Okay? How else can we slice this thing?
Angle.
At an angle. Where? Like through it like this?
No. Yeah. So let's just cut like halfway through the triangle angle.
Halfway through the what?
Halfway through the triangle angle.
So more like this.
Yeah.
Okay.
We have a rhombus.
So this is a circle, completely horizontal. If we get just a slightly pitched line, oh, I meant to make that a different color. I just drew if you're wondering, I just drew a black line on there, which is hard to see.
oh, I just-
Barely. No, make it a better line than that. All right. So if I took that line and it just went right through and sliced it just through like that, three-dimensionally, can you imagine what that might look like?
Rhombus.
Well, a rhombus has straight edges. A rhombus is a four-sided figure that has all sides the same length. All right? But we're going to have a curved edge because it's a cone.
It'd be a circle, wouldn't it?
Well, it's not going to be an exact circle when we
Semicircle?
were like this. Yeah, so this was a complete circle when we were completely horizontal. A little bit of an angle like that, and we're going to get an oval. And we'll actually have a more specific word that we use to describe that. What if I took this and sliced it right there? Nope, not even. Like I am right at the very tippy top.
Why would that change?
What would it be? If I went right to the top of the cone and I just hit the very, 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 very tippy top.
Oh, would it be like a parallel?
It's just going to be a single point. Because think about a cone. At the very top of the cone, it just ends right there at the tippy top. If I only catch just that fraction of a top, it's a point. If I take this line, and if I just, with my plane, it's actually, I'm like slicing it, right? So it's like a plane that I'm slicing it with. If I just slice the edge, what shape is that? It's a line. And then, what if I go like this? This gets to be a little harder to imagine. If I go vertical, but it's not through the center. When we did vertical through the center, we said that was a triangle. But if I go vertical through an edge piece there, so again, imagine that inverted ice cream cone, and not through the center, but just off the edge, you just sliced it off. What would that look like? Yeah, it would kind of have like this upside down U shape. All right, and then really, even if I do like this, it's going to have another U shape. So in all of these are what are called my conic sections. And it might be hard to read down here, but we did this one. So technically, a conic section, when they started coming up with this idea, is they said, well, what if I take a vertical line, and I take that line, and I put a point in the middle of it, right there. And then if I take, let me move the line. It's not gonna let me move the line. All right, undo. So if I take that line, and if I take that line, so look at me here. This is a better way to go. If I have this vertical line, pretend this is a vertical line, right? if I take this at this point, put it at an angle, and then rotate it around, I'm making the upper cone and the lower cone. All right, and it has its own name, but it doesn't matter. But that's how they come up with what are called conic sections. The conic sections, if you can't read, that says circle. So if it's completely parallel to the base, it's going to be a circle. If it's slightly off, we had the oval, but we call that an ellipse. E-L-L-I-P-S-E, ellipse. If it's at an angle, but specifically that angle is parallel to this, so slicing it somewhere here or lower, we get what's called a parabola. That's the quadratic that we've been dealing with. That's a parabola. And if it's completely vertical, it's going to intersect down here and up here. It's what's called a hyperbola. And then the other geometric shapes happen as well, right? If we just slice it where they come together, that's a point. If I slice it just off the edge, that's a line. So I've got points and lines, and then I have circles, ellipses, parabolas, hyperbolas. Those are my 4 conic sections. And we'll spend some time today doing what it is that we want to do with that. But before we do, let's hit a couple review questions. All right? Take a moment and solve this using the quadratic formula. Now, if you don't have the quadratic formula memorized, you're looking it up quick. All right, giving you some time to do it. Let's start with this. What is A? A is 2. What is B?
12,
12. And what is C?
46, -46.
Negative 46. Very important when doing all these. Always keeping track of those positive. If any of those are negative, you got to make sure you translate them over as negative. So we'll do x equals, make sure you have your calculators ready, so when you need to do calculations, you know what we're doing. So negative 12, because it's negative b, plus or minus square root b squared. I'm just going to go ahead and write that as 144. It's one of those that I have memorized. Minus 4 times a, which is 2, times c, which is negative 46. All over 2a. So this will be negative 12 plus or minus square root of 144. What is negative 4 times 2 times negative 86?
368.
It's positive or negative? Positive 2.
No, 3.
368.
Yeah.
368. Anybody want to confirm that number? Yep, I got bobbleheads confirming. All over 2 times a. And a, by the way, I didn't write it in there. A was 2, so 2 times 2 is 4. X equals negative 12 plus or minus square root of 144 plus 368, 512. All over 4. Now we're going to go to simplified radical form. To do that, I'm going to take the square root of 512 and think of numbers that go into 512 that we know the square roots of. And it's better to start big. I mean, if you start with 4, you can. It's just going to take us a while to go there. So I'm thinking of, right, 4, 9, 16, 25, 36, 64. 6 to 64 go in there.
Yeah, with
8 times. 64, I chose that because I know its square root. The square root of 64 is 8. It equals 8. Do I know the actual square root of 4? Or sorry, actual square root of 8?
4.
I do not. So I choose 2 numbers, one of which I know the square root of. 4. Square root of 4 is 2, and this over here is 2. Again, every time we're doing this, these two numbers multiply to that. These two numbers, 4 and 8, 4 and 2 multiply to 8. And I keep going down until I get to numbers that are either prime or numbers that I just can't take the square root of. I cannot take the square root of 2. So the square root of 512 is equal to 8 times 2 times the square root of 2, which is 16 square root of 2. So here I rewrite this as 12 plus or minus 16 square root of 2 all over 4. Over 4 plus or minus 16 square root of 2 over 4. Reducing. And I treat that 2, that square root of 2, kind of like a variable. Like I can't do anything with that, what's inside of there, but it's like saying I had 16x over 4. Well, the 4 and the 16 can reduce because they're whole numbers, but I can't do anything reducing with this. You can't take a 2 out of that with the 4. So final answer, 3 plus or minus 4 square root of 2 equals x. Those are my two solutions to that equation. All right. That's a parabola up here because it's a squared value. At 3 plus 4 square root of 2 and 3 minus 4 square root of 2, those are the two locations where the parabola crosses the x-axis.
It would be a because of the -12.
Oh, yep, thank you for pointing that out. The negative is here. I lost the negative in that step right there. Negative, negative, negative. Yes, negative 3, 4 square root of 2. All right. Logarithms, did this a couple times in the last week and a half. Does that equal 4? Explain. Take a moment. Again, look at your notes if you have to. All right. Calculators can't do log base 3, which is on purpose for why I select a problem like this.
Cut the short.
So generically defined, log base b of y equals x. That's a logarithm. We did converting back and forth. Which is my base? B. So as an exponent, it would be b to some power up here. When looking at this, trying to remember which one is which. So that's the base. There's an arrow. That's the base. This one is what? That's the exponent. So it would be b to the x equals And then in an exponent form, that would be the, answer. Or what it equals. This and this are mathematically the exact same thing. This is drawn as exponents form. This is put into logarithmic form. So in a question like this one up here, when I ask, are they equal?
Yes.
My explanation would be what then if you say yes? So you're saying yes
I'd say
because
3 to the power of 4 is equal to 81.
3 to the power of 4 equals 81. All right? A variation that could happen on a question like this would be if I intentionally wrote it with numbers that work, but in the wrong spot. So that way, if you don't remember this, you're going to go, oh yeah, 3 to the 4th, that's 81. So the wrong answer would be yes. The correct answer on this one will be no, because 3 to the 81st power is not 4. Remembering that whatever the log equals, that's the exponent. 3 is the base. 3 is the base. Base down here is b. All right. So being well-versed, practicing this, example problems on your note card that you can have for your final exam. For the final exam, you're probably going to be looking at, many of you wanting a front and back for listing things, having examples. And as I've stated before, and I think some of you have watched and have realized this, having an example problem is one thing, but having words telling you what to do in those steps is probably the more important part. Because on the exam, you're going to forget. Oh, how did I do that again? So you have words in there saying, I did this, and this is why I did the next step, and this is why I did the next step. Those are the more important aspects to problem solving, is knowing why you're doing what you're doing, not just saying, oh, I can recreate that. So now, an extension of what we did with logarithms before is solving an equation where my exponents include the variables. And up here on the right-hand side, I have included a remembrance of what those properties of logarithms are. When two logs are added, I can rewrite it as logs multiplied. When a log is subtracting, that's the single log of division. When a logarithm has something raised to a power, that power scooches out in front. That b comes out in front to multiply. All right? And there's some other aspects of what we covered too, more in terms of identities. We practiced some of these. Log of 10. All right, well, log of 10 is really saying 10 to what power is 10? So log of 10 is 1. The natural log of e is 1. Because natural log is log base e. So e to what power is e? Well, e to the first power is e. 10 to the first power is 10. Those are my identities in logarithms. How that relates to exponents, x to the 0 power is 1. Similar idea. All right. So when I'm solving an equation here, and my exponents are here, to eliminate the 10, which is my base, I'm going to rewrite it as a logarithm. Log base 10, which we normally don't write, it's just a regular logarithm. Log base 10 of what goes in here, that's what the problem is answering, which is 1, equals the exponent. So when we converted on that previous slide, the exponent is what the logarithm is equal to. X squared minus 3x minus 4. Now I go to my calculator. What is log of 1? Do it on your calculator so you know how to use your calculator. What is the log of 1? Remember, if you're using your phone in class here, you can't use that on the exam, so have out your actual calculator so you're using it the right way. What is the log of 1? Zero. If you're wondering, how is it 0? 10 to what power is 1? Well, anything to the 0 power is 1, so 10 to the 0 power is 1. So log base 10 of 1 is 0. Now I have a quadratic. The super short and simple way of thinking about that is, since my first term is 1x squared, I can just do x and x. Then I'm thinking two numbers that multiply to negative 4 that add to negative 3. Numbers that multiply to negative 4, if you want to, we can list them. Negative 4 and 1, 4 and negative 1, 2 and negative 2. Which pair adds to negative 3, the middle term? The first set. This is my set that works for that, which means it'll be x minus 4 and x plus 1. I have two items right here, this and this, that are multiplying to equal 0, which means either x minus 4 equals 0 or x plus 1 equals 0. Add 4, x equals, not 0, x equals 4. Add 4 to both sides. Or on the other one, x plus 1, so we subtract 1 from each side, x equals negative 1. Those are the solutions for that problem. If I were to graph this, the quadratic, the parabola intersects the x-axis at 4 and at negative 1. All right. Next thing we're going to do with this problem, I'm going to shrink this up, is we're going to find the vertex. The reason why we're going to find the vertex is, 1, to practice that aspect, but also 2, later today when we're on the notes here, we're going to be finding the centers and vertices of my quadratic functions. So if I have this original equation of x squared minus 3x minus 4 as a parabola, so y equals, I'm going to find the vertex of that parabola. And the process is using completing the square. So to find the vertex, we will complete the square. Completing the square, first step in that is I move my variables, my x's to one side and the numbers to the other side. Or in essence, I'm going to take this 4, got to move it to that side, so I add 4 to both sides. Y plus 4 equals x squared minus 3x. Now I have the x's all by themselves. The completing the square method is I take half of the middle term, so half of negative 3, which is negative 3 over 2, half of negative 3 over 2, and I square it, and I add it to both sides. So over here, I'm going to add the same thing. Negative 3/2 squared. Middle term was negative 3. Half of that is, well, divided by 2, so negative 3/2 squared. Over here, negative 3/2 squared. Negative 3/2 squared for the left side is 9/4 plus 4, which I will do, let's see, 16 and 9, so that's going to be plus 25/4 equals, and on the right side, I'm going to factor that. But I don't have to go through all the steps of factoring. I'm not going to go through the Xbox method. I'm not going to do anything else. Completing the square allows me to directly rewrite this as x minus 3/2. So what this number was, half of b goes right in there. And that whole parenthesis set is squared. And now I'm done because this is vertex form. You just have to remember what that means. Like we've done with a lot of types of problems, when we leave it, I say, okay, what makes this 0? What makes that 0? What would make this 0? What would I put in for y that when added to this would make this whole side 0? Negative 25/4. Is that all right? Because they're additive inverses. They add to 0. So whatever makes this 0 is the y coordinate of the vertex. What makes this 0? Positive 3/2. That is the x coordinate of the vertex. I don't have to worry about the squared. Nope, squared has nothing to do with it. In standard form, let me select everything. We'll move this up a bit. Y minus h equals x minus k squared. There's actually an a out here in front. We just didn't have one, or ours was 1. So this is standard form, where it's y minus h. Well, this is plus. This is minus. So what the difference is, that's why I say what makes this 0. So subtracting is adding a negative. So this would be plus a negative, and it's negative 25/4. This is y minus k. It is already minus, so it's just the straight 3/2. So if you can't memorize that, we just stay with that whole idea of what makes it 0. It's a concept we've used when finding the zeros or finding the x-intercepts, finding the solutions to quadratics, in this case now finding the vertex for a parabola. And this will carry over when we do a circle, hyperbola, and parabola. Oh, we just did the parabola. Ta-da. That's the vertex. Those are the points where it hits the x-axis. That's the vertex. So if I had to graph it, I could do that and just kind of visualize here quickly what that would look like. It'd be like, all right, like this, -1, +4. My vertex is somewhere down here. 3/2 is 1.5, so I went 1.5. Point. It's a parabola that comes down, curves, hits, goes back. Something like that. All right, so now we're going to deal with this as we do the different conic sections with the parabola, the circle, the ellipse, and the hyperbola. So here's the parabola. We just did that. Except what I did in the previous one is I called this A. It's actually 4P, and that's something that we're not going to worry about in our class. If you take pre-calculus next, you will deal with the 4P and figuring out where the directrix is. So again, a little foreshadowing if you're taking pre-calc next. Whenever you find that number, you set it equal to 4p, and then p will mean something for what you're doing. For us, it doesn't matter. All right, but we wrote it the other way. Y minus k equals a times x minus h squared. All right, this is what we're going to be dealing with for our course. So to do that, we are going to, here's an equation that's not in the form that we're used to seeing. So we're going to find the vertex of that using the completing the square method. So first thing first, I need to get it set equal to y. I'm going to add 6y to both sides. I will have then 6y plus 3 equals x squared minus 8x, just like that. So now I'm going to complete the square. I'm going to over here add half of the middle term. Well, the middle term is negative 8, so half of negative 8 is negative 4 squared. On this side over here, didn't leave myself enough room. I'll move my equal sign a bit. So I'm going to add negative 4 squared to both sides. On the left, 6y plus, all right, well, negative 4 squared is positive 16. 16 plus 3 is 19. This then equals x minus 4 squared. The purpose of doing the completing the square, once I find half of the middle term, that becomes the number inside the parentheses. This would factor into exactly this, x minus 4 quantity squared. Now it's almost in vertex form. Y minus k equals a times x minus h squared. It's
Sorry to interrupt. Braden, can I steal you for just a sec, dude? You're not in trouble. It's not in trouble. Just a sec.
all right. That was odd. It's almost in this form. What's different is the y has a number in front of it. So I need to get rid of that number, and I do that by factoring. 6, parenthesis. So I'm dividing each of them by 6. Y plus 19 sixths. All right, so if I divide each of them by 6, divide that one by 6, it just get the y, but the 6 comes out front. And then here, 19 divided by 6 is 19 divided by 6. Equals x minus 4 squared. All right. Then the last thing I'm going to do is I'm going to divide this whole thing by 6 and this whole thing by 6. These 6's reduce, leaving me with y plus 19 sixths equals, dividing by 6 is the same as multiplying by 1/6. So my a is now 1/6. X minus 4 quantity squared. My vertex, what makes x minus 4 0? 4. What makes this 0? Negative 19 sixths. That's my vertex for my parabola. And if you're curious, what does the 1/6 tell me? It tells me that my parabola is going to be really kind of squatty and fat. It does not go up fast. All right. Now we're going to do it for a circle. So there is the generic form of a circle. What you're going to see a little bit different. So now in a circle, instead of a vertex, we're going to have the center of the circle is H, comma, K. And we'll do the same thing when we get to that place. What makes this 0? What makes this 0? But then we also have this over here. Based on your past experiences of circles, if you have an R, what does R stand for? Radius. So R, just R by itself, is the radius. So when we're working on these problems, once we get this figured out, if we take the square root of it, that'll tell me the radius of the circle. All right, so this is the general form. The center of the circle will be H, comma, K, or in other words, what makes that 0, what makes that 0. And then whatever number I have all by itself over here will be the radius. So here is a circle. How do I know it's a circle besides the fact that I just told you it's a circle? Here's what I look at. The x squared term. So if you're wondering, and this will be part of like what you're going to be tested on for the exam. You're going to be given an equation, and you're going to be told, what is it? And explain how you know. This has an x squared and a y squared, which means it's not a parabola. The x squared and the y squared have the same sign. This one's positive, this one's positive. Again, on the same side of the equation too. The x squared and y squared on the same side of the equation. They both are positive, and the number in front of them is the same. That makes it a circle. All right, I'll repeat that one more time, just so you got it. How do I know it's a circle? The x squared and y squared on the same side of the equal sign. They have the same sign. In this case, they're both positive. If they're both negative, it could still be, but they're the same sign, and the coefficient in front of the y squared is the same as the coefficient in front of the x squared. In this case, they're 1. Doesn't always have to be 1. If they're both 2 and 2, it would still be a circle. So here's what we're going to do. We're going to use the completing the square method, but we're going to do it by grouping. So I'm first going to take the x squared minus 2x, and then I'm going to do the completing the square. I'm going to add half of the middle term. What's half of negative 2? Negative 1 squared. Then I'll have plus y squared plus 6y plus, I'm going to do the same thing again, half of the middle term. Half of 6 is 3 squared. Equals, and I have the negative 6. And then whatever I did, so remember we have equations. If I do something to this side, have to do the same thing to this side in order to keep my balance. I added this, and I added this to the left. So I need to do the same thing on the right. So I'm going to add negative 1 squared, and I'm going to add 3 squared. So once again, it's the completing the square method. Half of the middle term for the x squareds. So negative 2, half of that's negative 1. Square it, I add it to the left. Have to add it to the right. Then I take the y's. Take half of the middle term, so half of 6, that's 3. Square it over, and then whatever I add to this side, have to add to this side. All right, lots of completing the square practice. On the left-hand side, this will factor into x minus 1 squared. That minus 1 is the value that becomes half of the middle term. This, my plus sign comes down right there. The middle term, half of the middle term was 3. So the y will factor into y plus 3 squared. On the right-hand side, I've got numbers now. Negative 6 plus 1 plus 9. Negative 1 squared is positive 1. 3 squared is 9. Let's see. 9 plus 1 is 10 minus 6 is 4. I have y plus 3 squared. X minus 1 squared. The center of my circle, I look to the x's. What makes that 0? Positive 1. 1 minus 1 will be 0. What makes this 0? Negative 3, because negative 3 plus 3 is 0. That's the center of my circle. What is the radius? Well, this is r squared in general form. So r is the square root of that. 2. If I were to graph these, at 1, negative 3, 1, 2, 3, that's the center of my circle. My radius is 2, so from this center point, if I go up 2, I can put a point right there. If I go to the right 2, put a point there. Go to the left 2, 1, 2, put a point there. Go down 2. So those are kind of like the top, left, right, and bottom, and then it's all the matter of like how good are you at drawing circles. Not too shabby for freehand drawing. So if I were to take this equation, put it into Desmos or some other graphing software, it will create that circle.
Will we have to know how to graph it on the test?
We will not know how to graph it on the test, no. Nope. What could be on the test would be, here is an equation. Here are 4 circles, A, B, C, and D. Which one is it? You would have to complete the square and then know which one is the center and which one's the radius. And then pick the right one. Probably more simply, it would be an equation like this. Another possibility could be, here's a picture of an item. It could be a circle, parabola, ellipse, hyperbola, and there's 4 equations, and you say which equation matches with the image that's there. And when we get to our last slide or 2 today, we'll go through a bunch of examples like that, so hopefully you're like, oh, it's this, it's this, it's this, it's this. Because there tend to be like this little flow chart of solutions for how to find the solution. All right, now we have an ellipse. What's different now is instead of it equaling r squared like it did for a circle, it equals 1. And then whatever's under these determines whether or not I have an ellipse that goes this way. It's not a very good ellipse. Let's see if it'll let me draw an oval. Yeah, it does. Or an ellipse that's like this. That's a circle. Got to make it much more pronounced as an ellipse.
Is this going to be on the final?
There we go. If it's a vertical ellipse, that meant the number under the y value is larger. If it's a horizontal ellipse, the number under the x is larger. So what will be on the exam is we're going to have an ellipse, and you have to identify it. Hey, this equation's an ellipse because of these things. And we'll go through it here in a second. All right. And we're doing the completing the square so many times today as a way to remember how to do it for parabolas, which you have to know. I got to think of the exam. I'm like 99% confident you're not going to do completing the square for an ellipse. So what we do today for completing the square is for practice, but being able to identify an ellipse is the bigger part for the exam. That was the general form of the ellipse. It has to equal 1. All right. This one I look at and say, because I've been doing this, longer than you've been alive, is an ellipse. How do I know it's an ellipse? Right? So the last one we said was a circle. Circle was if they're on the same side and they're both positive, which they are. To be a circle, the number in front of the y squared has to be the same as the number in front of the x squared. They're different. So when the x squared and y squared are on the same side, they're both positive or both negative, and the numbers are different, now it's an ellipse. Circle, same side, both positive, both negative. Same number, circle. Same side, both positive or both negative. Different numbers, ellipse. And then my process is complete the square. I'm going to take this, have x squared plus 2x plus half of the first term, or half of the middle term, so half of 2 is 1, and square it. Then I'm going to take the y's. It's a little bit different now. I have 4 and 24. I need the y to be 1. So I'm going to factor a 4. 4 y squared minus 8y. Now I take half of the middle term. That's not 8, that's 6. (24) divided by 4 is 6. I'm going to make that green. Come on, undo, there we go. 6. So then half of the middle term is negative 3 squared. On the right side, I have negative 3 plus the negative 1 squared. And here's the tricky part. I don't add this to this side, and here's the reason why. This number, because I factored out the 4, this number includes the times 4. So on this side, I will be adding 4 times negative 3 squared. When I factor that 4 out, that meant whatever goes on inside will have to be multiplied by 4. So if I were to multiply this back out, I'm actually adding this whole amount to that side. Completing the square. This will be x plus 1 squared, because that's a positive 1, plus 4 times, this factors to y minus 3, quantity squared. And on the right side, help me with the math there. So 9, 3 squared is 9, 9 times 4 is 36. 36, if you look, I actually didn't bring down 33, I just brought down the 3, sorry about that. So 36 plus 1 is 37. 37 minus 33 is 4. Did I do my adding and subtracting correctly? Hopefully you're checking me. Yep, good, good, good. So now, on this equation, how do I make this a 1? X plus 1 squared over 4 plus, well, these 4's reduce, so I have y minus 3 squared over 1. You can leave it over 1 or you can not. It wouldn't matter. Now it equals 1. So that means the center of my ellipse is, what makes this 0? X plus 1, so x has to be negative 1. What makes this 0? Something minus 3. That's 3. And again, if you're going to take pre-calc next year, or next term, this tells me that the horizontal axis of my ellipse is longer than the vertical. So this would be a horizontal ellipse. It would look kind of like that. And the center of that would be at negative 1 comma 3. So if you're curious, this length here is going to be 1. This length here is going to be 2. From the standard form, this was a squared, that was b squared. So if a is square rooted, that's that length. B square rooted is that length. You don't need to know that. That's just fun facts. It's math. It's patterns. So again, what you need to know is I can look at this and say, yes, it's an ellipse. And I know it's an ellipse because the x squared and the y squared are both positive, but the coefficients in front of them are different. That makes it an ellipse. What you do have to know for the exam is how to do completing the square, which we've done a couple times here.
What if they're both negative?
If they're both negative, it would also be an ellipse, if the numbers are different. The hyperbola. So the hyperbola is the one that kind of goes graphically, it's going to look like this and like this. So kind of like an upside down and right side up parabola. Now they should be identical in their shape, and they're not. This is more parabolic and less hyperbolic. Because it actually spreads out a little bit more. That's what a hyperbola would look like. And a hyperbola's center will be right here. It's actually not in the middle of anything. So when the center there, it's going to be, again, h comma k. But we look, and it looks a lot like the ellipse function equals 1. The big difference is it's minus. In the ellipse, this was positive. I need it to be 1. How do I make it 1? So here we go. I look at that equation, and you have to identify what type of a conic section is it. And I look and see the x squared and the y squared. This one's positive, this one's negative. At that point, my only option is that it's a hyperbola. If they are opposite signs, it has to be a hyperbola, period. Can't be anything else. If they're same sign, could be a circle or an ellipse. But for a hyperbola, if one of them is positive, the other one's negative, has to be an ellipse, or has to be a hyperbola, I mean. All right, guess what we're going to do next? Completing the squares. I'm going to factor a 4 out of this. I will have y squared minus 4y plus half of the middle term squared. And I forgot to say this. Since this is not an x or a y, I'm going to actually move that to the other side. So I'm done. I'm going to have the 1 on the other side. For the next one, since it's negative, I'm going to factor a -1 from each term. So negative x squared, factor out that negative, it's now positive x squared inside. Negative 2x, factor out the -1, it's positive 2x. And now I will add half of the middle term, half of 2 is 1, and square it. Equals 1. That's the 1 over there. I added 1, moved it over here. And then I need to take these two things. This -2 squared is inside the parentheses. So I'm going to be adding not just -2 squared, but also times 4. 4 times the -2 squared. And then on the other one, I'm not just adding the 1 squared, I'm adding it times the negative. So it's going to be plus a -1 squared. So I'm really subtracting over there. On the left, 4, parenthesis, y minus 2 squared. Y squared becomes y. The -2 squared is just -2. Minus x plus 1 squared equals, now I'll have 1 plus, let's see, -2 squared is 4. 4 times 4 is 16. 1 squared is 1 and subtract it, so -1. So this whole side over here is 16. 16 plus 1 minus 1. How do I make this 1? Divide by 16, divide by 16, divide by 16. My equation then will be, see, these reduce to 4. Y minus 2 squared over 4 minus x plus 1 squared over 16 equals 1. It's a hyperbola, and the center is at, here's the x. What makes that 0? -1. What makes this 0? +2. And that's the center. Hyperbolas can go either like the one I drew, like vertical and like up and down. Hyperbolas can also go right and left. If you take pre-calc, this will tell you, depending on which one's positive, which one's negative, will tell you which way it goes. And then these numbers on the bottom will determine some asymptotes. It's a little bit more complicated graphing technique. All right, so here we go. They're all set equal to 1, but that doesn't mean anything in this case. It means it could be a hyperbola. Could be. So the conic sections that we have to think about are a parabola, a circle, an ellipse, and a hyperbola. And then we look at these and we say, which one is which? Are there any of them in there that can only be one thing? Right? So when you look at these over here, like what's a characteristic of a parabola that's none of these other things? What's a parabola when we think about the equation? Do you remember the general form of the equation?
It's subtracting rather than adding.
A parabola,
Y minus.
y minus h equals a times x minus k squared. How many things are squared? Are the x and y both squared?
Yes.
Is there a square on that y?
No.
No. Is there a square on the x? yes, it's outside the parentheses, but the x eventually will be squared. The y is not. So if I look through any of these, do any of them not have one of the variables squared?
Last one.
The last one. Since there are no variables squared on the last one, this is a parabola. All right. For the hyperbola, what was the thing I said has to be true for a hyperbola?
They have to be different signs.
The x squared and the y squared have to be different signs. There's a minus, there's a minus. Is the y being squared? Yes. Is the x being squared? Yes. There is a negative, which means this has to be hyperbola. Let's look at the other one that's minus. Is the y being squared? Yes. Is the x being squared? Yes. Are they opposite signs? Yeah, this one's positive because there's nothing. This one's negative. This one is also a hyperbola. For the circle, we said they're either both positive, both negative, and the number in front of the x squared and y squared is the same. I've got two left. Which one do you think is the circle?
Third one.
The third one. And the reason why is because these are the same. So if I multiply by 16, this will be 16 over here. So this will be my circle, but what I'm going to do is if I multiply everything by 16, I will have y minus 2 squared plus x minus 1 squared equals 16. My radius will be 4. That's the square root of 16. The center will be at 1, 2. But yes, this one here is a circle. I can't multiply by one number and have both of the, if I multiply by the lowest common denominator, which is 36, I'll have a number out in front, and then I'll have a number out in front. So these numbers are different. They're both, they're both positive, different numbers. This is then the ellipse. So we looked at the example problems that I did where we did completing the square, where we showed examples of, oh, here's one. What is it? It's this. Because of the x squared and y squared were the same sign, but they had different numbers, it was an ellipse. And then now we're looking at it like this, where they're all kind of in a basically same looking format, and then talking through the same rules for each of those and deciding what's here. So again, for the exam, this, or what we did on each individual slide and identifying, how do I know what it is? That's the most important part of deciding which goes with these. All right. You should also know what they look like. A parabola will be on an XY axis in just one single arch. A hyperbola on a graph could look like this. Where it's like two arches, either going horizontally or vertically in opposite directions. A circle, that would be something I would hope you know what a circle looks like. And then an ellipse, for lack of a better word, is an oval. Center. And some of you might be wondering, why are conic sections important at all? Conic sections actually model a lot of things that happen in the world. For example, the parabola. All of you have been near a parabola recently. One of two different ways. So there is a point on the parabola called the focus. And it's usually right about there. See that little dot that I just drew? Right there. That's the focus. So here is the fun fact about the focus with a parabola. That focus, if I were to take anything that operates in a wave, so sound waves, light waves, like waves, and if at that point I have, like if it's a sound wave, if there's a speaker, every sound wave that leaves that speaker and hits the edge of the parabola bounces this way. If I have a sound wave that goes like this, it also goes directly out that way. If I have one that hits here, it goes directly that way. If I have one that goes way out here, it goes that way. So that all of those waves are all now going in the same direction. So probably not going to be a speaker that you've had, but probably the headlight of your car. Your headlights of your car are meant to go, for the most part, straight out in front of you. Well, how do I get a light bulb? Because if you ever have a light bulb in a house, you just put a light bulb in, it goes everywhere. So how do they focus that light so that it all goes forward? Because you don't want light going backwards. You're losing all that light. But if you ever pull out a light bulb of a car, you'll see it shines light out of all the sides. Well, what it does is it has a giant reflector inside there, so the light that comes out the back side of your light bulb goes like this and then goes straight center. So all of these lights go like this. Now, the light that comes out the front that misses the edge of the parabola, so if I have some light that goes just this way, it misses the edge of the parabola of my actual light. That's what creates the light out on the edges of your headlight. And that's why it kind of gets diffused out there. It's not as bright. But the stuff in the middle, that's the brightest because that's what's reflecting straight away from that inside of your headlight. All right, so that's a parabola. An ellipse, I don't know if anybody knows anybody who's ever had a kidney stone. Kidney stones are very painful. They're usually made out of calcium. They develop inside of your kidney. And then if you're not familiar with your anatomy, from your kidney to your bladder is your ureter. And then from your bladder out is your urethra. So your ureter, the tube that goes from your kidney to your bladder, is narrow. And it hurts badly. So I've only had one. I hope to never have one again. But now, present day, if you need to have kidney stones removed, they can do it surgically, arthroscopically. They send a little thing up, you're out. They go to it and they zap it with a little tool, and then they grab it and then they pull it out. But you do it under anesthesia so it doesn't hurt. Yep. If you have to pass it naturally, it's a jagged stone that goes through and basically makes small cuts in your ureter and hurts a lot. But before they had surgery, this is what they did. They would sit you in a tub that was in the shape of an ellipse. An ellipse. Here's the center of the ellipse. An ellipse has two foci. Right there and right there. And here's the fun fact about a foci. If you had something that emits waves out of one focus, wherever it hits the edge, it will reflect directly back to the other focus. If it comes out here, it reflects back directly to the other focus. And every point where that happens, even if it goes like this, you're like, oh, it goes way out to that edge, then it bounces directly back here. So here's what they would do. They would fill this tub with liquid that's in the shape of an ellipse. There would be a chair right here. They would have you sit in that chair and get your kidney right where that focus is. And have you sit in the tub. At that focus, they had a speaker. The speaker emitted low frequency sound waves, like very low. Now, if you've ever been in a car, near a car that has a big subwoofers, can you feel the bass hit? Yes. When you drop even lower outside of your sound range, you can feel those waves even though you can't hear them, if they're very much directed exactly at you. So these sound waves would be very low frequency, would hit there and would go this way. Sound waves go through your body. You can feel them with your soft tissue, but sound waves stop when they hit something hard, like say a kidney stone. So it goes through your body, they hit the little kidney stone, and the kidney stone's like, it vibrates. That's me imitating a kidney stone. They don't actually make sound. But and they vibrate, and then they shatter. Because they're not very hard. It would not damage the rest of your stuff because the rest of your body in that area is all soft tissue. So it's just going to like move and flow and you'll feel it. Anyways, so now your kidney stones break up into smaller pieces so that they're small enough to go through the ureter.
So basically what you're saying is heavy rock and roll music.
Are you familiar with the old TV show called Mythbusters?
Yes.
Okay.
Do they sell these speakers? I want to put one in.
Yeah, no, they don't sound speakers like this. Well, I mean, if you can get a speaker and then you can get something that just broadcasts a tone, and then you just dial the tone down to a low enough frequency. But this is to the point. There's what has been referred to as the brown note. So it's a frequency of sound that's very, very low, that theoretically, if you faced it at someone at just the right low frequency, it actually inspires your bowels to move. That's why it's called the brown note. It makes you poop your pants. And so the Mythbusters spent time figuring out, is there such a thing as the brown note? And again, why would that be an important thing? Actually being developed by the military.
So they're gonna.
Because if you suddenly have troops somewhere and you want to temporarily incapacitate them all, you send the brown note and they all suddenly have to poop. Now, more realistically, it's not for troops, it's for dispersing crowds. So if you have a riot going on,
That's actually smart.
what is a great way to make rioters leave? They all of a sudden are like, oh, I gotta crap my pants.
Without actually harming them?
It would not harm you, no, but it would make you all have to defecate at the same time.
I would use that for interrogation.
Oh my god.
All right? Well, we won't talk about interrogation. So the ellipse and the parabola are two things that actually have a lot of possible applications. The same thing holds true. I mean, circles are in a lot of places too. Hyperbola is a little bit more complicated, but their existence has some deeper meanings in some areas of physics. Has anybody ever been to Washington, D.C.? Yeah?
Wait, so did they figure out it was real?
In the Capitol building, well, you can figure that out on your own. This is why you have Google. All right, in the Capitol building, where the Congress used to meet, now they have a congressional side of the facility, but where they originally met was in an oval room. And in that oval room, and we're talking like Thomas Jefferson, early founders kind of days, right? In this oval room, there would be the one group of politicians that would meet at one end, the other ones would meet at the other end, they would meet in the middle for debate. When they're here, they're talking about strategy. Well, it was one of these politicians that was a mathematician that realized this is an ellipse. And so he set up his desk right here.
So you can listen to everyone.
And then they would be over here discussing their strategies. And he would just sit and listen. And even though there was a ruckus of noise in this entire room, If he sat there and just focused on the small voices, he could actually hear all of their conversations over here. So that way, when they would come together for a debate, he already had responses to all of their debate topics before they even showed up. People thought he was just a brilliant debater when the reality was he was a mathematician. I mean, well, he recognized that it was the ellipse and that their sounds could be heard. So if you ever take a tour there, you will actually go into the rotunda and they will have the group stand here, and then the tour guide goes over here and he'll say something to you and then come back and you're like, yeah, we heard you say some phrase or something like that. So you have to know whose voice you're listening for, because there's a lot of other people in the building talking. But it's just because of the way all the sound that he would say here goes directly to you over here.